Have a look at page 3. Let's have a look at page 3. June 15 P42. Okay. This one would be question 10. Okay, that is what is meant by specific acoustic impedance of a medium. The part where here I mentioned to you is actually talking about Z equals to rho C. It's just the product of density of the medium and the speed of the ultrasound in the medium, or speed of sound in the medium. So as I mentioned to you, C is not the speed of light, so don't ever write it as the speed of light. Okay, so this one is all right. Just copy again from your notes. Now for part B, the specific acoustic impedances Z of some media are given here. Right, A, gel, soft tissue, bone. The density of a sample of bone is 1.7 times 10 power minus 1.7 times 10 power 3 kg per meter cube. Right, determine the wavelength in millimeter of ultrasound of frequency 9 times 10 power 5 hertz in the bone. They want you to find out what is the wavelength of the ultrasound given that you have this frequency. So wavelength and frequency, the first thing that might come to mind is this equation. V is equals to F lambda. You know the frequency, you want to find the wavelength, but you're missing the speed of ultrasound, or rather the speed of wave inside the medium. Okay, they tell you that in bone, your ultrasound has frequency of this much. You want to find the wavelength. You're just missing the speed of the ultrasound inside the medium, inside bone. So to find out what's the speed of ultrasound inside the medium, inside the bone, you need to make use of your definition of specific acoustic impedance. Z equals to rho C. Your specific acoustic impedance of bone is already given to you as 7 times 10 power 6. You also know the density of bone. From here, you can find the C. This is the speed of ultrasound in bone. From there, you can use V equals to F lambda and subsequently find out what is your lambda. Okay, you get your answer as 4.58 millimeter. Okay, so if this one is fine, then we can just move on to the next one. Right, so this one I assume no problem. Okay, right. Now, ultrasound of intensity I is incident normally on the boundary between two media or specific acoustic impedances. Z1 and Z2 as shown in figure 10.2. There's actually two mediums here. This is medium 1, sorry, this is medium 1, this is medium 2. You see there's Z1, Z2 here. Okay, to tell you the intensity of the ultrasound reflected from the boundary is IR. Okay, which is given by this expression. By making reference to data for air, gel, and soft tissue, explain quantitatively why during medical diagnosis using ultrasound, a gel is usually put on the skin. Right? So basically what you have here is this is your boundary between the two media. Alright? So your ultrasound hits the boundary, part of it was reflected, which is this one. And they tell you the ratio IRI is given by this. It is actually talking to you about the fraction of intensity reflected. Now they ask you by making reference to data for age and soft tissue, explain quantitatively. This one means you need to show calculations. You need to show calculations and numbers. Right? So explain quantitatively why during medical diagnosis using ultrasound, a gel is usually put on the skin. This one I did kind of mention to you just now. When you wanted to put your ultrasound transducer, if you just put it directly like this, I mentioned to you that you would have a layer of air. So if you had a layer of air, your fractional intensity reflected would be very large. So instead what you do is that you put a gel so that your intensity reflected is very small. So that was the basic idea I told you. If you're using gel, your intensity reflected would be very small. But if it's just air, your intensity reflected will be very large. Okay, so that was what I explained. Here, you're trying to explain the same thing, but you're trying to prove it with calculation. You're trying to show actual numbers here. So you can actually do something like this. This is ultrasound. This is also ultrasound. Okay. So you can consider two cases, air tissue boundary and gel tissue boundary. So you're trying to sum in the values and work it out. So give you the time to do that. So this one is okay. So this is gel tissue. This is air tissue. Okay. So work it out and you should get this answer. The values of the Z you will have gotten it from here. A and tissue, gel and tissue. Right? So try to work it out. Please remember to square your answers accordingly. Right? Now when it comes to using this one, the ones that I wrote here was Z2 minus Z1 square, then Z2 plus Z1 square, right? Here they wrote Z1 minus Z2 square, Z1 plus Z2 square. It doesn't really matter the ordering, okay? It doesn't matter. And also, you don't really need to be so occupied about whether should it be the smaller value minus the larger value or larger value minus the smaller value. Because at the end of the day, even if you get a negative answer, it will be squared. So the negative is essentially eliminated. They will have gotten rid of the negative. So it won't really matter. Whether should you take a smaller value minus larger or larger minus smaller, it won't matter. The negative will just be eliminated when you square it. Okay. So at some point when you do this, you should be getting this answer already. For air tissue boundary, you're getting a ratio of 0.99999. That means you have a lot of intensity reflected. For gel tissue boundary, you're getting 1.04 times 10 power minus 3, which is actually 0.00104, which is very little intensity reflected. Okay, so you have shown this. So you just need to write some statement to explain. For air tissue boundary, there is almost complete reflection of your ultrasound because the ratio is close to 1. No ultrasound is transmitted into tissue, which is not good because, as I mentioned to you, your ultrasound needs to go into your medium, into your body, and it needs to go deep so that it can give you the reflection so that it can produce an image. If there isn't any remaining, that means it cannot go deep, it cannot give you any image below your skin. All right. So for gel tissue boundary, there is little reflection. There is almost complete transmission of ultrasound into tissue. So in your case here, this is good because your ultrasound can keep on going deep into your body and keep on giving reflection so that it can produce an image with even more detail because you have multiple reflections, right? So this is your answer. This one is, I believe, page 3. If page 3 you're okay while you're copying this, if you're done, you can also have a look at page 12. Okay, so if this one is fine, then we move on to page 12. Page 12 would be this one. And after that, you have this. Okay, right. This is June 16 P41. Again, this one is question 4. So just have a look at that. There are some parts that I will just skip now because it's something we've already done. Alright. Now what is meant by specific acoustic impedance? We've done this just now, so I'll just skip this one. It's the product of speed. It's the product of the density and the speed of wave in the medium. That's all. Now then after that they ask you the intensity reflection coefficient alpha is given by this expression. Z2 minus Z1 square over Z2 plus Z1 square. You see, even here, they also sometimes are not consistent, which is which. Previously, it was Z1 minus Z2 square over Z1 plus Z2 square. Now this one is the other way around, Z2 minus Z1 square over Z2 plus Z1 square. So it actually doesn't matter. All right. Now explain the meanings of the symbols in this expression. What is alpha here? So alpha here is actually the fraction of intensity reflected, because here you know that it is IR over I, right? Okay. Ratio of reflected intensity to incident intensity. Okay, here I don't put the naught lah, I naught. I don't put the I naught, I just put I lah, so that it's a bit consistent, right? It is the ratio of reflected intensity to incident intensity. All right, and what is Z1 and Z2? This is the specific acoustic impedances of the media on each side of the boundary. Right, so that one is okay. Then if you're okay with that, then have a look at the other question, right, which is this one. All right, now for part B, they tell you that you have a parallel beam of ultrasound with intensity I naught as it enters a muscle. The beam passes through a thickness of 3.4 centimeter of muscle before being incident on the boundary with a bone. The intensity of the ultrasound beam as it passes into the bone is IT. Some data for muscle and bone are given here. This is the linear absorption coefficient. This is the specific acoustic impedance. Calculate the ratio of IT over I. Okay, now this is where you need to be careful of it. Now, there are two mediums here. One of it is muscle, one of it is bone. They have told you that what is here is your I naught. Then after that, what is here is your IT. Now, there is one thing you needed to know. Remember just now I told you when your ultrasound is traveling through a medium of a certain thickness, its intensity will actually drop because it will be absorbed as it passes through the medium. So whatever you have here, upon hitting the boundary, this is your boundary here, you do not say that it is equals to I naught. It will not be the same. Okay, whatever you have here, it will not be the same as I naught because you have attenuation. So here you need to consider the effects of attenuation. From here to here, you actually have attenuation. your intensity here would not be the same as the intensity here. It will be some value, which is IM. Maybe I just represent it by symbol IM. This intensity here, upon hitting your boundary, there will be some reflection, some transmitted. Okay, they didn't tell you the full story here. They only told you bits and pieces of it, but you're supposed to recognize that whatever intensity you have here is going to be different from here because of reflection. And then upon hitting the boundary, there will be one portion that is transmitted, one portion that is reflected. Okay, this one will be like this. Okay, so let me just do that. Okay, right, so now that you're clear on that, then we can look at this. Now they ask you to calculate the ratio of IT to I naught, this to this. So you have to consider a few things first, right? So from the workings here, I want to consider what is IM first. Okay, now if I wanted to get IT over I naught, there's no direct method in getting it. I cannot use IR equals to Z2 minus Z1 square over Z2 plus Z1 square. I cannot use I equals to I naught exponential negative mu x or kx directly, because this one, IT and I naught, is neither fraction reflected nor fraction remaining after attenuation. Okay, but you know that IT over I naught can be rewritten as this, isn't it? IT over I naught is actually IM over I naught multiplied by IT times IT over IM. Now, you see, if I do this one here like this, the IM will cancel off, giving me IT over I naught. It's like you applying chain rule here in maths. You find two different fractions to get the other fraction you want. Okay, so now you know that IT over I naught can be given by this. This one, you will notice, tells you something. This one is fraction transmitted at boundary. IT over IM is actually the fraction transmitted at boundary. Then after that, you look at IM over I naught. This one is the fraction remaining after attenuation. Okay, you need to find these two ratios now. Now for fraction remaining after attenuation, which is IM over I naught, this one you can easily just use equation I equals to I naught exponential negative mu x. Basically the absorption through the muscle, or you can just write the attenuation through the muscle. So you can find out the ratio of IM to I naught straight away from the data that is given to you. You need to find out the mu for the muscle, the thickness of the muscle. Eventually you get this. In your case here, when you want to use the mu x, you don't really need to change the, you need to change some of the things. Your mu is in per meter. Your thickness, you need to change to meters also. Your thickness of your muscle is 3.4 centimeter. You need to make sure you change it to meter because your mu is in meter. Okay. So this one is what? 3.4 centimeter. And then this one here is, they just give me 3.4 centimeter there. Okay. So eventually the ratio you get is 0.4575. So far so good. Now then after that, you want to get the fraction transmitted at the boundary. Now recall that just now earlier in the chapter for ultrasound, I made mention to you that fraction of intensity transmitted at boundary is going to be equals to 1 minus IR over I. It's going to be equals to this. It is actually under page 13 of your notes. I mentioned this. I explained how you got this. If you want to talk about the fraction of intensity transmitted at boundary, you need to take 1 minus fraction of intensity reflected. Fraction of intensity reflected is something you can find now. The IR over M, which is your alpha right now, you can find. Okay, just take the values of the Z and then minus it off, square it, plus it, and square it. Now the 10 power 6 will actually cancel each other. Also, I actually didn't put it inside here. Alright. So eventually you get your fraction of intensity reflected at 0.3306. Now the fraction of intensity transmitted would be 1 minus alpha. So it will be 0.6694. So now you have two of the ratios already. You have this one and you have this one. So you multiply them together and you get your answer as 0.306. Okay. Right. So far so good. Yeah. There's a reason why this question is worth 5 marks. Yeah, it's a lot of things to consider in one shot. All right. So if this is fine, then the next question that you guys can have a look at is actually on page 16. All right. The next question you guys can have a look at is actually page 16. All right. So if no problem, I will just go to page 16. All right. Okay. So have a look at page 16. Oh, this one again. Page 16, November 16, P42. Okay, this one will be question 5. Okay, now ultrasound may be used, this is page 16. Okay, now ultrasound may be used to obtain information about internal body structures. Suggest why ultrasound for a transducer is pulse. Okay, just now I mentioned to you that ultrasound must be pulse, right? So that in the end you get something like this. This one here is what you get, right? This one here was what I mentioned, your transmitted pulse. This is your reflected pulse. This one was your reflected pulse. The reason for that is because you want to get your time delay, which gives you info about the depth of your boundary. Remember the depth of your boundary. And then after that, another thing also is because you want to get the intensity reflected. The intensity reflected would actually give you your nature of boundary, correct? So you getting back your reflected pulse gives you two information. The time delay will give you information about the depth of the boundary, and then after that your intensity reflected will give you information about the nature of the boundary. This one if the ultrasound is pulse. Okay, this one is if ultrasound is pulse. What if your ultrasound is continuous? What do you think will happen? If your ultrasound is continuous, it will look like this. If your ultrasound is continuous, your graph will look like this. Let me just draw this. Your graph will just look continuous like this, right? It's just a continuous line like this, right? You cannot determine any info about reflected ultrasound. Okay, if your ultrasound is continuous like this, your pulse that is reflected will actually be buried by your transmitted ultrasound. It will be embedded inside, so you cannot really see what was the time delay, and then you won't be able to see what was the intensity of the reflected ultrasound. So you cannot really determine anything useful out of it. Remember just now I told you that for ultrasound, you need the reflected pulse to produce an image of your body structure. You need to know the time delay, you need to know the intensity of the reflected pulse. If in your case here, your ultrasound is continuous, your reflected ultrasound will actually be buried by your transmitted ultrasound. You cannot see what was the time delay, you cannot see what was the intensity. You can't do anything, you won't be able to get anything useful. So hence the thing is that you need it to be pulsed. Only then can you clearly see it. Okay, so the answer here will be something like this. A transducer both transmits and receives ultrasound. It receives reflected pulses between emitted pulses. Your ultrasound needs to be pulsed in order to determine depth and nature of boundary. Okay. So ultrasound is used both as a transmitter and receiver, because normally if this one was your tissue, your ultrasound transducer is this. This one is your ultrasound transducer. It will transmit ultrasound and it will receive back the ultrasound. It is the same device that transmits ultrasound, it is the same device that receives back the ultrasound. This is the transmitted ultrasound, this is the reflected ultrasound. The same device is actually transmitting it, the same device is actually receiving back the reflected ultrasound. Okay, so if your transducer is both transmitting and receiving, it's actually doing it at the same time. So if it's doing it at the same time, this is what you get if the ultrasound is continuous. But if you pulse it, then there won't be this issue here. You get this instead. Okay, it's supposed to receive the reflected pulse between the emitted pulses. So then you can actually see this. All right. State what is meant by specific acoustic impedance. We've done that just now, so I'm just going to skip that. It's the product of speed of ultrasound in the medium and density in the medium. Okay. Okay, now if you have a look at part 2, okay, part 2 talks to you about a parallel beam of ultrasound intensity I0 is incident normally on the boundary between two media as shown in figure 5.1. Okay, the media has specific acoustic impedances Z1 and Z2. The intensity of the ultrasound being transmitted across the boundary is IT. The intensity of the ultrasound being transmitted across the boundary is IT, yeah. Explain the significance of the magnitudes of Z1 and Z2 on the ratio of IT to I0. Okay. All right, now for this particular case here, again, it is talking to you about explaining the effect of the magnitudes of Z1 and Z2 on some sort of ratio. Now, the one that you were used to talking about just now was IR to I naught, the fraction of reflected intensity. When you look at this one here, this one is one medium, this one is one medium, this is your boundary here. Okay, they say that this is your incident intensity, this is your transmitted intensity. When this one hits your boundary, there's supposed to be a reflected intensity, IR. The fraction of reflected intensity, IR to I naught, will be given by this. But the question here, you read carefully, is talking about the ratio IT I naught. They're not asking you about the fraction of reflected intensity. They're asking you about the fraction of transmitted intensity. So this one, they're asking they're asking you about the fraction of transmitted intensity, not reflected. So now you need to explain your Z1, Z2 based on that. Okay. Now, what you understood was this, right? If you're referring based to the fraction intensity reflected, if your Z1 and Z2 are very much same with each other, the difference between them is considered to be small. So your IR will be small, but in return, your transmission will be large, right? Your reflection is actually inversely related to your transmission, isn't it? Because we told you that I naught is IR plus IT. If your IR increase, your IT will drop. Likewise, if your IR drops, your IT will increase. They are inversely related. So if we wanted to explain, you could just look at this one first. If Z1, Z2 were the same, the difference between them will be very small. The reflected intensity will be small. But then in return, your transmission will be very large. If on the other hand, your Z1 and Z2 are very different from each other, that means the difference between them is very large. Your reflected intensity will be large, and in return, your transmitted intensity will be small. So you want to use your explanations of Z1, Z2, but to explain transmitted intensity now. Okay, so hence your answer was like this. Okay, if Z1 and Z2 are nearly equal, by right, intensity reflected will be small, but transmitted intensity will be large. Transmitted intensity, or the fraction of intensity transmitted, will be nearly equal to 1. There's little reflection and mostly transmission of ultrasound. If on the other hand, the difference between Z1 and Z2 is very large, you know that the reflected intensity will be very large, but the reflected intensity will be small. So the fraction of intensity reflected is nearly equals to 0 or just very small. There is mostly reflection and little transmission of ultrasound. Okay, so that is your answer here. Okay. Right, there's actually only 4 more questions for ultrasound, but this one I think I have to complete it the next lesson. The next few questions that you could have a look at was page 8, 9, 18, 20, and 31. Okay, right. So this one is okay. Just let me have a look at page 9 first. Page 9 is the one with the complicated calculation. Right. Okay, right. So I think I would just probably... Alright. This one you guys are okay already. So you can just copy this. Okay. Right, if you just look at page 9 of your medical imaging chapter, that time we stopped at ultrasound. So page 9 is an example of how complicated an ultrasound question can get. So if the question says right now, you have a parallel beam of ultrasound that's inserted normally on the surface of a layer of fat of thickness 1.1 centimeter as shown. For the ultrasound, they give you these particular variables. I1 is intensity just after entering the surface of the fat layer. I2 is the intensity incident on the fat muscle boundary. I3 is the intensity reflected from the fat muscle boundary, and I4 is the intensity received back at the surface of the fat layer. And then the data for the fat is given here, where they gave you specific acoustic impedance, density, and absorption attenuation coefficient mu. So they're asking you calculate the time interval between a short pulse of ultrasound initially entering the layer of fat and then returning back to the surface of the layer of fat. Okay. So in your case here, Alright, now we are in page 9, right? Of medical imaging. Okay. Yeah. So back to this simple question here. Calculate the time interval between a short pulse of ultrasound initially entering the layer of fat and then returning back to the surface of the fat layer. This is fat. Your ultrasound enters, then it gets reflected. They want to find what is the total time taken for the ultrasound to enter and then returning back after reflection at this part. So logic will tell you you can actually just use that speed over distance time. Speed is equal to distance over time. You need to know the speed, you need to know the distance, only then can you find out the time. So in your case, for the ultrasound that is traveling in the layer of fat, you can actually find out what is speed because you know that specific acoustic impedance Z equals to rho C, where Z of the fat is 1.4 times 10 power 6, density of the fat is 940. This will then tell you what is the speed of the ultrasound in that medium in fat. So you get the speed as 1.49 times 10 power 3 meter per second. You know the speed is this much. And then after that, what is the total distance traveled? Here they told you it's 1.1 centimeter. The difference between them is 1.1 centimeter. So what you will have here is 1.1 centimeter. Okay. So this 1.1 centimeter, your ultrasound, it traveled this length towards the boundary and then it got reflected back towards the surface. So your distance traveled is actually twice of 1.1 times. Is actually twice of 1.1 centimeter, right? So now this one is your equation for speed equals to distance over time, time being distance over speed. The distance is twice this distance. Your speed is this speed. You eventually be able to get out what is the time taken. The time taken is actually just 1.48 times 10 power minus 5 seconds, right? So this one should be okay. This is like AS level kind of questions. Then we go to the next one where they ask you to calculate a few things now. They ask you to calculate the ratio of I2 to I1. Okay, calculate ratio of I2 to I1. Now, before you go to that one, there are some things that you need to identify from here. You see, if I'm talking about I1 and I2, because it traveled through this layer of fat, it's gonna have a portion of its intensity absorbed by the fat. You're gonna have attenuation. So from here to here, you have attenuation. Decrease in intensity of the ultrasound after it's traveled through the layer of fat. Then once your ultrasound reaches here and it hits the boundary between fat and muscle, you know that for ultrasound whenever it hits the boundary between two different mediums, it will have a portion that is reflected and a portion that is transmitted. So in your case here, your I2 is the intensity of ultrasound hitting the boundary of the fat muscle. layer. This one here being your boundary. Okay, so from what you learned last week, whatever intensity you have here, it will be split into a portion that is transmitted and a portion that is reflected. So here you will have, you're supposed to have intensity, you're supposed to have intensity transmitted, and then you're supposed to have intensity reflected. This is the intensity reflected. Okay, this and this came from this. But in your question here, they didn't tell you about this now. They just told you I3 here. I3 being the intensity reflected from the fat muscle boundary. So this one here actually came from this after reflection. So here you have another thing to consider. This is reflection. Okay. Then this I3, the intensity of ultrasound that is reflected, it will go back through that same medium. It will go back through the same length. A portion of its intensity will still be absorbed by the medium. It will have decreased in intensity to become I4. You again have in your case here attenuation. Okay, so it's important to realize when your ultrasound is coming in here from the beginning, you went through attenuation, you went through reflection, and you went through attenuation again. These are the three main things that happen to that intensity I1 when it move about, when it move through the layer of fat. So for your case here, when they were talking to you about I2 to I1, this is a summary of that diagram there. When they ask you what's the ratio of I2 to I1, I2 to I1, this one, as I mentioned to you, this is actually the result of attenuation. I2 is the remaining intensity after I1 has been attenuated. So when it comes to attenuation, you know that there's a general equation that you can use, which is I equals to I naught exponential negative mu x. This is for attenuation. So here, your initial intensity, this one will be I1. Your remaining intensity will be this one will be I2. Okay, this one was initial intensity, this is the remaining intensity. So applied to your current diagram, it will be I2 equals to I1 exponential negative mu x. So the ratio of I2 to I1 is exponential negative 48 times 1.1 times 10 power minus 2. This one you need to remember to change your units so that they're consistent. Your mu here is in meter, so your x must also be in meter. Alright, so you change it so that the units are the same, so that they cancel off. So your final answer will be 0.059. Sorry, 0.590. Okay, so this is what you will get. Answer being 0.590. Alright, then I will just go on to the next one if possible. Just erase this. Okay, if this one you're okay already, then we go to the next question. Now, they tell you intensity I4 is 0.33% of intensity I1. Determine the ratio of I3 to I2. What they basically just gave you here is that they told you I4 is 0.44% of I1. Okay, sorry, not 0.44, 0.33% of I1. And then they tell you from this information you have, find out the ratio of I3, I2. Now, for your case here, this one you can actually make out some sort of expression where we tell you I4 to I1 is equals to, basically what's this now? I4 to I1 is like this. We tell you I4 to I1 will be I4 to I3 multiplied by I3 to I2, I2 to I1. Okay, that is one way in which you can get some sort of useful ratio here. But before I go to that, maybe it's better if I just draw something out here first. Say for example, I give you 3 different mediums. This one is a separate thing. This one is medium 1, this is medium 1. Maybe I don't do this. Maybe I give you, in your case, 3 different mediums. 1, 2, 3. And then I give you a case where you have different intensity. This one is probably I1. This one is I2. And this one is, maybe I just do this. This one is I2, this one is I3, and then this one is I4. This one is I3, and then this one is I4. Wait, sorry. Something is inconsistent. Okay, this is a simple illustration. I1, I2, I3, I4. Okay. So now this one I can say that this one will go through attenuation, this one will go through attenuation, this one will go through attenuation. This one, say for example, is just X-ray lah. We don't talk about ultrasound first. We don't talk about ultrasound. I talked to you about this case here being 3 different mediums, and I talked to you about this one being X-ray. So this one enters the medium is I1. By the time it wants to enter the second medium is I2, and then after that, once it enters the second medium, goes through medium 2, so the second medium is intensity reduces to I3 before entering medium 3. And then once it enters medium 3 and it passes through it, it becomes intensity I4. Okay. Now this one here, I could say that maybe for example, this one is, if I want to get this ratio here, I4 to I1, I4 to I1 is the same as I4, I3 times I3, I2 times I2, I1. You see there's something like a pattern here. If I want to get this ratio to this ratio, it'll be equals to this ratio multiplied with this ratio multiplied with this ratio. It'll be I4 to I3, I3 to I2, I2 to I1. Then eventually you see that this will cancel off, this will cancel off, eventually giving you back that same answer. Right? If you are able to find out what is this ratio, you're able to find out what is this ratio, and you're able to find out what is this ratio, you'll be able to find out the ratio between the final to initial intensity. So the same could also be said for this one here right now. If they really give me the intensity I4 to I1, this one being my final, this one being my initial, I know that I4 to I1 will be the same as the ratio of I4 to I3, I3 to I2, I2 to I1. Okay, that is the idea here. Because if you do that, eventually you notice that they will all cancel each other off. So I4, I1 is I2, I1 multiplied by I3, I2 multiplied by I4, I3. You'll see that I2 will cancel off, I3 will cancel off, giving you I4, I1. Okay, so you want to get the ratios for each of this. You multiply them, you get back this ratio. Okay, but the thing is that they've already actually given you the ratio of I4 to I1. What they want to find instead is actually the ratio of I3 to I2. This is what they want to find. Now this one, I4 to I1, you already know what's the ratio. It's 0.33 divided by 100. Because this is in percentage form, you want to change it to fraction. And then your I2 to I1, you actually already found it. It is 0.959. This one you already found it as 0.59. Okay. Now there's also another thing here. you will be thinking I4, I3 you do not know, right? But you see the I4, I3, I can say it's actually the same as I2, I1. I can actually say that I4, I3 is the same as I2, I1. I4, I3 is the same as I2, I1. The reason is because you are traveling through the same medium. Just now I drew for you here that your I2 to I1 is result of attenuation. I4 to I3 is also the result of attenuation. The ratio that you have here which is I2, I1, I4, I3. This one was actually the fraction of remaining intensity after attenuation. Okay, because this and this, by right, this is just talking to you about fraction of remaining intensity after attenuation. Because you're talking about them going through the same medium, they should have the same ratio. If here right now I2, I1, you get a ratio 0.59. This one just tells you that after going through attenuation in this direction, whatever intensity you have will be 0.59%. So it will be 59% or 0.59 of your initial intensity. If I tell you this one is I2, this one is I1, I2 to I1 being 0.59, this one tells me that this one will be 59% of this or 0.59 of this. Likewise, if after reflection I get I3, then I get I4 here, this one will also go through attenuation. Because they're traveling through the same medium, the fraction remaining will be the same as this one here. This one will be also I4 will be 59% of I3 or I4 will be 0.59 of I3. Okay, so they would have same values. All right, so this one and this one will just be 0.59, 0.59. Okay, right. So that one here I told you is fraction of intensity remaining. This one here is fraction of remaining intensity. Now I3, I2 you can actually deduce out what it is also. This one will be useful in your next question. I3, I2, if you look at your question just now, I3 is this one, I2 is this one. Just now I mentioned to you, this is your I2 hitting the boundary between your media. So you will have a portion transmitted and a portion reflected, right? So this one, I3 to I2, is actually your fraction of intensity reflected. Okay, so this little part here, the I3, I2 that they're asking you to find is actually the fraction of intensity reflected. Okay, so the first and third is fraction of intensity remaining after attenuation. The second one, the middle one, is fraction of intensity reflected. All right, so you know the values of the three ratios here. You know this one, you know this one, you know this one. You can now work out what is I3 to I2. Okay, so let me just work this one. Okay, this is what you get. You eventually get I3 over I2 as 9.48 times 10 power minus 3. Okay, so this one is fine. Okay, so this one is okay. Then I move on to the next one. Okay, now the specific acoustic impedance of muscle is greater than that of fat. State the effect, if any, on the value of ratio I3, I2 of an increase in the difference between the specific acoustic impedance of muscle and fat. So Just now the question told you that you had fat here, and then you had muscle here. All right. So what was mentioned was that fat and muscle have their own specific acoustic impedance. Maybe this is Z1, maybe this is Z2. So as mentioned to you just now, this one being the boundary between the two media, you would have a portion that is transmitted. You will also have a portion that is reflected. Okay. So just now I mentioned to you the fraction that is reflected is I3 over I2, right? The question is asking you about I3, I2 right now. The I3, I2 just now, as I explained to you, is actually referring to your fraction of intensity reflected. Okay, I3, I2 right now, you should be able to see from the diagram, is actually referring to the fraction of intensity reflected. So when it comes to fraction of intensity reflected, that time I mentioned to you a few things about it, right? IR over I being Z2 minus Z1 squared, Z over Z2 plus Z1 squared. Whether your fraction intensity reflected will be large or small depends on the magnitudes or the difference between Z1 and Z2, right? Isn't it? So what was generally mentioned to you was this. If the difference between Z1 and Z2 is small, meaning to say they are very similar to each other, the intensity reflected will be small because this one will be small, this one will be small, this as a whole will be small. Okay? If the difference between Z1 and Z2 is large, meaning to say Z1 is very much larger than Z2, the intensity reflected will be large. Simply because if one of them is larger than the other and you minus them, the difference will be very large. This expression will be large. This one here will be large. So your expression as a whole will be large. Okay. So in your case here, they tell you specifically that the difference between the specific acoustic impedance of muscle and fat is bigger now. Meaning to say the difference between them is bigger. So you actually would expect the intensity reflected to be larger. And I3 to I2 being fractional intensity reflected, you will be able to say that ratio of I3, I2 will actually increase. Okay? So that is one thing here that you need to kind of get. All right? So you have to understand that I3, I2 is actually the fraction of intensity reflected. Okay?